When you hear teleportation, your mind probably jumps straight to Star Trek. Captain Kirk dissolves into a stream of shimmering particles and rematerializes on a distant planet moments later. For decades, that's been the dream, zapping matter across space instantly. But what if I told you that teleportation is real? It's happening right now. Now, before you start packing for an instant vacation, let's be clear. We're not beaming people around. The reality is actually far more revolutionary, and it's happening through the very same internet cables that are bringing this video to you. Scientists aren't moving atoms, they're teleporting information. They're instantly transferring the fundamental essence of a particle, its quantum state, from one place to another, without that particle ever crossing the space in between. This isn't just a clever trick. This is the dawn of the quantum internet, a new network built on the mind-bending laws of quantum mechanics. It promises an unhackable, interconnected world and will power computers that could change everything. This is the story of how a sci-fi concept became an engineered fact, paving the way for a future that will be faster, safer, and more powerful than we can even imagine. The problem, our fragile digital world. Before we get to the quantum solution, we need to understand a chilling truth about our own digital world. Nearly every part of our lives, banking, healthcare, private messages, even national security, is built on information flowing through a global network. And that foundation is terrifyingly fragile. Think of today's internet as a global postcard system. When you send an email or buy something online, you're essentially sending a postcard with your information on it. We've gotten very good at writing these postcards in a secret code, a process called encryption, and for decades, that's been our main defense. Most of that encryption relies on a simple piece of math. It's easy to multiply two huge prime numbers together, but it's incredibly hard for a regular computer to take that massive result and figure out the two original primes. A modern computer might need billions of years to crack a single standard encryption key. That's the lock on our digital doors. But that lock is about to be picked. A new kind of computer is coming, a quantum computer. It doesn't play by the same rules. It runs on the bizarre principles of quantum mechanics, allowing it to chew through vast amounts of information in a way that's fundamentally different from a classical computer. An algorithm designed for these machines, Shor's algorithm, can solve that impossibly hard math problem with terrifying speed. A powerful enough quantum computer could theoretically break a standard encryption key, the kind used everywhere online, in a matter of hours. Every secure system we rely on would become wide open. This has created a new threat known as harvest now, decrypt later. Hostile groups are already capturing and storing huge amounts of our encrypted data today, betting that in the near future, they'll have the quantum key to unlock it all. Every secret, every financial record, every piece of classified intelligence sent today could one day be as easy to read as a morning newspaper. The very tool we built to connect the world is facing a potential quantum apocalypse. To fight it, we can't just build a better lock. We need a whole new kind of door. And the answer, it turns out, lies in harnessing the very quantum mechanics that threatens to undo us. The Quantum Solution Part 1, the qubit. To understand this new, unhackable future, we have to start with its basic building block. In a classical computer, all information boils down to a simple bit, a 1 or a 0. It's a light switch, either on or off. Our entire digital world is built from endless strings of these on or off switches. The quantum world has the qubit. A qubit isn't just a light switch, it's more like a dimmer switch. It can be a 0, it can be a 1, or it can be both at the same time. This strange property is called superposition. The easiest way to picture it is to imagine a spinning coin. While it's spinning in the air, it's neither heads nor tails. It's in a superposition of both possibilities. Only when it lands and you measure it does it collapse into a definite state of either heads or tails. A qubit works in much the same way. Until you measure it, it exists in a cloud of probabilities, holding the potential for being a 0, a 1, or a mix of both. This ability to exist in multiple states at once means a single qubit can hold exponentially more information than a classical bit. 2 qubits can hold 4 states at once. 3 qubits can hold 8. As you add more qubits, the processing power grows exponentially, which is what gives quantum computers their incredible potential. But holding more information is only part of the story. The real magic, the property that makes teleportation and an unhackable internet possible, comes from a second quantum phenomenon, one so strange, it famously bothered Albert Einstein himself. The Quantum Solution Part 2, Entanglement. In 1935, Albert Einstein and his colleagues wrote about a consequence of quantum theory they found deeply unsettling. It described how two particles could become linked so that they behave as a single system, no matter how far apart they are. A change to one particle would be mirrored instantly by the other, even if they were on opposite sides of the galaxy. Einstein famously, and dismissively, called it spooky action at a distance. Today, we call it quantum entanglement, and it's the absolute heart of quantum communication. Imagine you have a pair of magic gloves. You put each one in a separate box without looking and mail one box to a friend in another country. The moment your friend opens their box and sees they have the left-handed glove, you instantly know you're holding the right-handed one. No message was sent between the boxes. The information, the perfect correlation, was already there. Entangled particles are similar, but much weirder. Let's say you have a pair of entangled photons. Before you measure them, neither has a definite property, like its polarization. They are like those spinning coins, existing in a superposition. But because they're entangled, their states are perfectly correlated. The moment you measure one photon and find its polarization is, say, vertical, you know with absolute certainty that its entangled twin, no matter how far away, will instantly take on a horizontal polarization. This is the spooky part. It seems to happen faster than the speed of light. But it doesn't actually violate physics because no information is being sent. You can't use this link to send a message. The outcome of your measurement is random. You can't force your photon to be vertical to send 1 to your friend. All you have is a shared, secret correlation. So if you can't send a message with it, what's the point? The point isn't to send information with entanglement. It's to use entanglement as a resource to teleport information that already exists. This is where science fiction becomes real. The breakthrough, teleporting information. So, how do you teleport something? It's a 3-step process that combines the strangeness of entanglement with a little bit of classical communication. Let's say our sender is Alice and our receiver is Bob. Alice wants to teleport the quantum state of a particular photon, let's call it photon X, to Bob. First, Alice and Bob need to share a pair of entangled photons. We'll call them photon A and photon B. Alice holds A, and Bob holds B. They can be miles apart. Second, Alice performs a special measurement on her original photon, photon X, and her half of the entangled pair, photon A. This action links them together, but it also destroys the original state of photon X. You can't clone quantum information, so the original has to be sacrificed. Third, Alice sends the results of her measurement to Bob over a classical channel, like a normal internet connection. This message is just 2 ordinary bits of classical information. When Bob gets these 2 bits, he knows exactly what to do to his entangled photon, photon B. He applies the right correction, and instantly, photon B transforms into a perfect replica of the original photon X, possessing its exact quantum state. The information has been teleported. No particle traveled the distance. Instead, its fundamental identity was destroyed in one place and perfectly reconstructed in another, all thanks to that spooky link of entanglement. This isn't theory anymore. In a landmark experiment in late 2024, engineers at Northwestern University did what many thought was impossible. they successfully teleported quantum states over about 30 kilometers of existing, commercial-grade fiber optic cable that was simultaneously carrying live internet traffic. The challenge was described as trying to navigate a bicycle through a crowded tunnel of speeding trucks, but by finding a quiet, unused wavelength of light, they proved quantum and classical data can coexist on the same infrastructure. The lead researcher, Prem Kumar, said, "This is incredibly exciting because nobody thought it was possible. It opens the door to pushing quantum communications to the next level." This single breakthrough changes the game. We may not need to build an entirely new physical internet. We can use the trillions of dollars of fiber optic cable already crisscrossing the globe. And the breakthroughs are accelerating. In late 2025, a European collaboration led by Paderborn University in Germany announced the first ever teleportation between two different quantum dots. Quantum dots are tiny semiconductor crystals that can emit single photons on demand. By showing they could link photons from separate sources over a free space link, they demonstrated the key principle behind a quantum repeater, a device that can one day extend entanglement over global distances. That same year, a team in Japan from Kyoto and Hiroshima universities achieved what's called W-state entanglement, developing a way to perform a collective measurement on three linked photons at once. This is vital for building more complex, multi-party quantum networks. Then, in early 2026, the race heated up again. A team at Shanxi University in China achieved something extraordinary. They teleported 5 quantum states simultaneously. Technically, these were commodes, not discrete qubits, but the achievement acts like increasing the bandwidth for quantum information. From a single state in a lab to multiple states over busy city networks, these breakthroughs are the foundational steps. The science is proven. Now, the engineering of the quantum internet has begun. The ultimate goal, the quantum internet. What does a world connected by teleportation actually look like? The quantum internet won't replace the classical internet we use for browsing websites or watching videos. Instead, it will work alongside it, as a specialized network for tasks that need its unique power. The most immediate application is unhackable communication. This is done through something called quantum key distribution, or QKD. Imagine Alice and Bob want to share a secret encryption key. They can do this by sending a stream of qubits. Thanks to the laws of physics, if an eavesdropper, let's call her Eve, tries to intercept and measure those qubits, she will inevitably alter their state. Alice and Bob can test a small sample of their qubits, and if they find any changes, they know Eve is listening. They just discard the key and start over. The security is guaranteed not by a math problem that could one day be solved, but by the fundamental laws of physics. This technology is already smashing records. In early 2026, a team from the University of Science and Technology of China, USTC, demonstrated the gold standard of QKD, known as device-independent QKD, over 11 kilometers of city fiber. This protocol is so secure that it works even if the communication devices themselves were built by the eavesdropper. They further proved its physical feasibility over an incredible 100 kilometers. This isn't theoretical security. It's practical, deployable security for connecting government buildings and financial institutions across a city. The second world-changing application is distributed quantum computing. Quantum computers are incredibly powerful but also difficult to build. The quantum internet will allow us to link multiple, smaller quantum processes together, wherever they are. Using teleportation to transfer qubits between them, they can function as one massive quantum computer, pooling their resources to tackle problems far beyond the scope of any single machine. This could supercharge the search for new medicines, the design of new materials, and the development of artificial intelligence. Finally, a global network of entangled particles could link telescopes across the planet, creating an Earth-sized observatory with the resolution to image distant exoplanets. It could create networks of hypersensitive quantum sensors for everything from more accurate GPS to early earthquake detection. The possibilities are so vast, we're likely only scratching the surface. We started with a science fiction dream of beaming from one place to another. What we've found is a reality that is, in many ways, even more profound. We aren't moving our bodies, but we are learning to move their fundamental information, their quantum states, across networks, all powered by the spooky action that so puzzled Einstein. We've seen the fragility of our current internet, threatened by the dawn of quantum computing, and the solution: a new network built on the bedrock of physics itself. We've seen how the qubit and its strange property of superposition, combined with the unbreakable link of entanglement, are the keys to this new world. And we've witnessed the breathtaking pace of recent breakthroughs, from teleporting information through the noisy traffic of our existing internet to transmitting multiple states at once. This is no longer a distant fantasy. Some experts project that the first commercial quantum networks and repeaters could begin to emerge by the late 2020s, with wider adoption and standardization for critical infrastructure happening through the 2030s. We are living at the inflection point where theoretical physics becomes engineering, and engineering begins to reshape our world. The quantum internet won't just make our information safer, it will unlock new frontiers in science, computing, and human collaboration. It represents a fundamental shift in how we communicate. The journey ahead is long, but the foundation is being laid, right now, through the very fiber optic cables buried under our feet. The next revolution is here. The question is, what will we build with it? What do you think is the most exciting application for an unhackable quantum internet? Let me know your thoughts in the comments below. And if you want to stay ahead of the curve on the technologies shaping our future, make sure to subscribe.